Hello, everyone, and welcome to another EE Engineering Training Days. I'm Amy Kalnoskis, Editor-in-Chief of EE World Online, and we bring you these EE Training Days a couple times a month. But today, we want to bring you a webinar sponsored by GORE on why enclosures fail, the role of venting in electronics reliability. So before we get to the good stuff, the really good stuff, let's get to the housekeeping stuff. Just little tools that are available for you all. There are resources that can be downloaded in the resource widget. Do check them out. You should see that little sign in the middle of your screen there. Lots of good information there from our presenters and our presenters company. And you can submit questions in the Ask Question widget. That can happen at any time while our presenters are speaking, during the official Q&A. And also, if you're watching on demand, you can still ask questions. And guess what? You'll still get answers. You can expand the slides with using that icon in the top right corner if you want to get the bigger picture. And just in case you have any issues, try refreshing your browser. That solves most of them. Make sure you close those other apps and browsers. They tend to be bandwidth hogs. And then you can always click those three horizontal lines in the top menu for troubleshooting steps if all else fails, or if you just need to communicate with our producer. You can also ask for help via the Ask Question widget. So before we get going, I would like to introduce our presenters from WL GORE. Let's start with Timo Seibel. Timo is an electronics application engineer from GORE and Associates. He has nearly 2 decades of experience in advanced filtration and venting technologies. He specializes in material solutions for electronics and energy sectors across EMEA. Timo brings deep technical insight and customer-focused innovation to every engineering challenge. Also presenting today is Matt Gessner. Matt is an electronics applications engineer, also with GORE and Associates, and he has over 28 years of experience in engineered polymer solutions. He applies GORE's materials to industrial, consumer, automotive, and mil-aero systems, focusing on gas pressure relief and environmental protection for NEMA IP-rated enclosures. He's a patent holder and contributor to standards in roadway lighting and industrial air filtration. So now we are going to get to the good stuff. I think, Timo, we're starting out with you.
Thank you, Amy, for the very kind introduction. Also from my side, hello and welcome to our webinar, Why Outdoor Electronic Enclosures Fail. This is the first webinar in our series around venting for reliability and durability of outdoor electronics. So as Amy already introduced, my name is Timo Seibel and I'm joined by my colleague Matthew Gessner. So we are both application engineers with the GORE venting business, and we have been doing this for quite some years now. Our main focus is outdoor electronics. So if you are working with devices that have to survive rough environments, you are in the right place with us. Before we dive in, let me quickly tell you a bit about us and what to expect from today's session. So GORE generally is a material science company, and we have been active in the outdoor electronics space for more than 35 years now. But the most people really know us because of GORE-TEX, the breathable and waterproof fabric that is used in outdoor shoes and jackets. But our materials go far beyond fabrics. They are inside your phone, keeping water out without messing up the sound quality, but they also prevent condensation inside car headlights and even keep airplanes connected through our high integrity cables. So with that, I think I want to say our materials are used in a very wide range of applications, making a difference everywhere, from everyday consumer products to highly specialized technologies. In the electronics industry specifically, our protective and acoustic venting solutions are trusted by some of the world's best known brands. They rely on them to enhance device performance while protecting against liquids, dust, and other contaminants that could otherwise damage sensitive components or degrade the performance over time. So this webinar will be about 40 minutes. And as Amy said, we will have time for questions at the end. The webinar is also recorded, and you will be able to download it on the EEE World website and on gore.com. With this said, let's start by looking at the bigger picture of electronics. So in order to understand why venting matters, let's take a quick look at how electronic systems have become such a big part of our world. It's probably no surprise to anyone, but our world is becoming more and more connected through electronic systems. We rely on them every single day, and that's not just for convenience, but also for our safety and security. Think about devices like security cameras, sensors, meters, lighting systems, Wi-Fi, and so on. Another big trend is that this equipment keeps getting smaller, more powerful, and it is expected that it runs 24/7 for many years without any failure. This is why it's so important that these systems stay operational and well protected from the elements. Because in most cases, failure simply isn't an option. The challenge for engineers is to ensure that those electronic devices stay protected and fully operational throughout their whole intended service lifetime. So when you think about how to ensure long-term operations of auto electronics, there are a couple of points to consider. We have listed a few examples here. So what is the environment it will be used in? Do the electronics require maintenance? What are cost constraints? What are the size or weight constraints? And does it have an IP or an EMA rating which needs to be fulfilled? All of these points, and maybe also additional ones which are not listed here, needs to be taken into consideration during the whole design phase. In most or maybe even all cases, auto electronics equipment is protected in some kind of weather-rated, sealed metal or plastic enclosure. But no matter how carefully enclosures are designed, they can still face challenges in real-world conditions and are sensitive to damages. Here are some examples of our most observed issues. If you look to these pictures, on the left we have condensation or fogging that won't go away and eventually leading up to liquid buildup. We also name this trapped moisture. In the middle and on the right, we see contamination from ingress of water, dust, dirt, or salt, and that is causing corrosion of the electronics over time. These are just a few examples of what can happen in the field. Now we are curious to hear from you if you have ever experienced similar issues like the ones that we are showing here. For this, we will open a quick survey and would like to ask you to provide an answer by choosing one of the options that are best matches your experience. So have you ever experienced issues in the field like corrosion, water, and ingress or trapped moisture? Please choose one of the options. I will keep it open for about 20 seconds. Yeah, I see the first answers are coming in. Yeah, let's have it open for a little longer. All right. Then I would go to the results. So I think we have a good mix. I see occasionally. That is great. You know, you have seen this before, and that shows how spread these challenges are. Also, I see never here. I mean, that means your enclosure is performing well. Maybe a vent is already in use here and ensures proper protection and pressure equalization. But still, I think it's good to know what can go wrong under real-world conditions, especially when you think about long-term exposure in really harsh environments. So next, I would like to take a look at the causes of these issues and what can be done to prevent them. So in a sealed enclosure, temperature fluctuations and rapid environmental changes, such as a summer rainstorm, for example, can create pressure differentials between the inside and the outside of the electronics housing. If this pressure is not equalized, moisture can be drawn inside and cause condensation. Over time, this problem can become worse. This constant pressure cycling can put a lot of stress on the seals, and that eventually can lead to a failure. And once the seal fails, contaminants like water dust, for example, can enter the enclosure and that in turn can lead to damages of the electronics and cause the whole device to fail. In order to avoid pressure buildups within the enclosure, you need to vent it and equalize any pressure changes that can happen. A pressure vent allows the air to flow in and out to the enclosure. With that, pressure differences caused by temperature changes or even altitude shifts can quickly be balanced. By doing this, the vent minimizes mechanical stress on the seals and ultimately helps the enclosure to maintain its protection. The result is a greater reliability and a long operating life of the device in the field. To better illustrate how pressure differentials happen, we have prepared a short experiment that simulates a very fast temperature shock. Here we have two enclosures of the same size that are IP66 rated and are made of die-cast aluminum. The one on the bottom is fitted with a membrane vent and the top one is unvented. The camera angle might seem a little bit different, but the test setup is actually identical. So we have heated up both boxes in the climate chamber to about 70 degrees Celsius before the cool down with the water jet starts. So now I will start a video clip which should pop up in your center field. So after this heat conditioning step, the boxes are sprayed with cold water for roughly 3 minutes. Probes inside the boxes measure the temperature and the pressure in real time. When the cold water hits the box, you can see the changes to temperature in red and pressure in blue on the graphs on the right side. The vented enclosure on the bottom is able to rapidly equalize the pressure, while the non-vented enclosure on the top sees a negative pressure spike of about minus 125 millibar. So over time, this negative pressure can weaken seals and cause failures. When considering a vent solution, there are a lot of options available. If you don't select the right one, you may end up with the same problems you were trying to avoid in the first place. So this chart here shows some of the most common solutions and how they perform against water and dust ingress, ability to pressure equalize, condensation management, as well as durability and ease of integration. You can see that some of those options work well at certain functions, but at others not so much. The best option for pressure equalization is an open hole, but then you have left the electronics exposed to the environment. Metal meshes do not offer much more protection than an open hole, and sintered metal vents can corrode over time. So when comparing solutions, protective membrane vents, like the one shown in the test before, have the best combination of features that ensure a long-term reliability for your enclosure. At first glance, a vent may look like a simple opening, but the membrane technology behind it is really what makes the difference. So let's take a closer look on how a vent works. The vent has a microporous membrane. Usually it's made of expanded polytetrafluoroethylene, also known as EPTFE. This material has billions of tiny pores that are large enough to let air and gases flow through, but small enough to block liquids, dust, dirt, and other contaminants. In other words, you can say the membrane is breathable to air, but it forms a reliable barrier against water and particles. When the pressure inside the enclosure rises, air can pass outward through the membrane. That will relieve the stress, and when the pressure drops, air from the outside can flow back in. This continuous exchange helps keep the internal pressure stable. But beyond equalizing pressure, the vent plays also a key role in controlling moisture. And moisture is one of the main threats to the reliability of electronic systems. So when humid air becomes trapped inside a sealed enclosure, temperature fluctuations can cause the moisture to condense into liquid water. Over time, this can result in corrosion, short circuits, or fogging of lenses and sensors. In order to avoid this, the vent allows the enclosure to breathe. Its microporous membrane, as we heard before, is permeable, but not just for air, also for water vapor. This enables moisture to diffuse in and out by nature. This continuous exchange again helps reducing the overall humidity inside the enclosure, and it keeps the internal environment being more dry and more stable. You can learn more about effective moisture management in our second webinar, which we will host together with EE World on November 20. With that, I will hand it over now to Matt. And please, Matt, go on from here.
Thanks, Timo. So Timo gave a great introduction on the consequences of not thinking about ingress protection. And he shared that vents can provide pressure equalization to protect your electronics from damage. So I will review how a vent solution can be matched to your enclosure requirements and how it can perform in these rigorous environments. The first step is to determine what your requirements are of your unique application. So we're going to use an example here of a vent design for an outdoor enclosure, specifically a camera. So a camera can be anything. It can be any other device, but in this case, the camera is outdoors in the rain and the sun. So we're going to start with some input parameters, such as the total enclosure volume, the operating conditions that are needed, and what the volume of air is inside the enclosure. So in this case, the camera will experience temperature changes from rain and snow and wind and heating from the sun. We're also going to assume that a high temperature of 70 C, but then it can rapidly cool to 15 degrees Celsius if there's a rain or snow event. So the enclosure size is going to be about 20, the enclosure pressure limit is going to be 20 millibar, and the size of the enclosure is going to be about 5.6 liters with a free air volume of 1.9 liters. So this is going to help us to determine what the seal limits are, and if you don't happen to know, GORE can provide that information to you. GORE uses a pressure response model to help project that pressure response during a weather or even an altitude change. The model uses the volumetric data that we mentioned and the changes in the ambient condition, along with a heat transfer function, to predict the pressure in the enclosure. The model allows us to compare different vent options to a fully sealed but unvented enclosure, assuming that there's no leaks. So if we have the model here that you see the inputs, you can see on the right-hand side, let me use my pointer here, that you can see that the output has these various responses. The red line here is showing a sealed but unvented enclosure, assuming no leaks. And this will actually, in that scenario of going from hot to cold, produce about minus 160 millibar, or about minus 2.3 psi of vacuum. Whereas with the three vent options you see here, it produces anywhere from minus 57 to minus 5 millibar, which is just under a psi or to 1/10 of a psi of vacuum. These pressure peaks can occur from 8 minutes with the sealed but unvented enclosure, but less than 2 minutes on the best option here, which is at the very top. So for the scenario, we would want to select a vent that is below this dotted line here, which was the limit of the minus 20 millibar pressure that we selected for our camera. So while the vent can equalize pressure in an enclosure from an outdoor environment or an altitude change, it must also keep out the dust and water that's going to be exposed to it during the lifetime of the device. We know that this is called ingress protection, or IP, and it refers to the measure of an enclosure's resistance to this dust and water and outside dirt. If you're not familiar with IP ratings, you can see there's various ratings on the chart here. Different standards organizations have different benchmarks, but these are the IEC IP code, which is pretty common for electronics in our space. The code is designated with the letters IP, and then there's 2 digits that follow it. The first is the dust protection level, and you can see it ranges from 0 to 6, with 6 being the most protected. The second digit is the liquid protection level. Now note that these are not necessarily linear, meaning that a higher number is not necessarily better. It's rather situational, specifically to the environment that's in. And I'm going to explain that a little bit more in the next slide. So let me first stop with a poll here and ask you, have you ever had to meet ingress protection standards in your design. Please click on yes, or occasionally, or rarely, or never. And I'm going to wait another 20 seconds or so for for you to answer. Okay, so I think we have some answers here. So let me go forward. So I see obviously yes frequently, and this is great. This is an opportunity for you to hear some important information. For those who have never considered it, I would suggest that perhaps this is an opportunity for you to expand into this area. Often customers will use a device and then find out after they've deployed it that they actually have some problems with dust and dirt and water. So I'd like to illustrate more about these IP protection tests and what's common in a protective vent. So we can actually break these up into three general groups: the dust protection, a spray protection, or an immersion challenge protection. So let's start with the dust protection, which is designated by the first digit. And on the left, we have a photo of an IP6X test, which is a dust challenge that actually pulls a vacuum into the enclosure through whatever the venting solution is. The dust here is actually a really fine talcum powder that's aerosolized over an 8-hour period. And you can't see, but there actually are holes on this photo that have a membrane vent underneath it. The second set of tests are related to that second digit. So this could be the IP4X, X4, X5, or X6. So that's the center challenge, which is the spray test. And this represents various levels of spray power. So IPX4 generally is like a light rain, so very low pressure. IPX5 is a powerful jet of pressure, and IPX6 is actually where you almost have a pressure washer. And that video that Timo showed earlier is actually an example of the IPX6 test. So you can tell that it was a pretty powerful spray of water. The last area of the immersion is seen on the right-hand photo, which is an immersion test. And so this can be either 1 meter for 30 minutes, which is IPX7, or higher than that. And the IPX8 is the next level up, but that can be determined by the manufacturer and the customer. So typically for GORE vents, we actually specify 2 meters of immersion for up to 60 minutes. So for our outdoor camera example, the IPX66 was required, or the high pressure spray. So after we've determined the pressure equalization need, then we can look at the various vent options and see which one actually can provide IPX66, or dust and high pressure spray. So now I'd like to revisit the slide that Timo had up earlier, showing the various vent options. So GORE uses the enclosure size and the environmental conditions to choose which membrane protective vent can be used to meet those pressure equalization needs. A sealed enclosure will not equalize pressure unless the seals fail and let the water and dust into the enclosure. The last page I showed what those tests are for dust and water ingress protection and how it needs to be used, how it needs to be deployed to actually meet those IP ratings. And these other vent options here cannot usually pass those tests. And as Timo mentioned, our next webinar will cover about condensation management. Now I would like to talk about some of those durability tests that are used to look at the lifetime of the test. So in the prior test, we talked about ingress protection for the environmental conditions, for the enclosure, but now we're going to actually add in some environmental conditions. So the IEC 600-68 has a series of environmental tests. These range from high temperature to low temperature dwell. And you can see that examples of these graphs here on the upper right and the lower left of a high temperature and low temperature dwell, with the vents placed in a chamber exposed to those temperatures for anywhere from 8 to 96 hours, and then run for the duration of the test, and then an IP test is run afterward. Another challenging test is cycling the temperature from cold to hot. And you can see on the lower right-hand side, a typical chamber graph, what the temperatures will have to be done. There's also a high exposure, high humidity exposure test that usually takes the vents and puts them into an 85 degrees Celsius at 85% relative humidity for up to 1,000 hours. So this is testing the durability of the membrane vent on the enclosure, and then later repeating the ingress protection test. Another test I'd like to spend a little more time on is the IEC 668 2-11 salt fog test. Now, the standard test actually takes the membrane vent and places it in a chamber, a salt fog chamber, which is producing 5% concentration of salt in a fog environment at 35 C. Now, this test runs for 28 days of exposure. And then after that, the enclosure is subjected to a IP test. What I want to do was actually go a little bit further and see what else we can learn about this test and how the vent is exposed and how it might perform throughout that test. So what I did is we looked at this vent over the period of the 28 days and actually looked at the airflow. And you can see that we did the initial airflow of the vent, and for material 1, we had a 480 milliliter per minute airflow, and material 2 was 1,468. Further, we pulled the vent out after 7 days to look at what is the airflow of that vent after it's been exposed to this high concentration of salt fog. And you can tell that the airflow did drop a little bit, 9% for each material. And you can see that there is a layer of salt that has formed on the vent. We continued on looking at this for the next 28 days. And you can see now that the airflow did drop initially at that 7 days, but then it did not drop any further. So that salt layer that formed was not actually getting into the vent. Further, after we exposed the vent for the 28 days, we want to simulate what it would be like for these membrane vents if they were washed down with a gentle rain. So we did a light wash down of the vent and found that it did recover at least half of the airflow from the initial. So we've seen now how membrane vents can be sized for the airflow of your enclosure and how ingress protection can be performed and under these lab tests, and how these tests can be used for looking at the robustness of the vent in a salt environment. I want to go through an actual outdoor environment and show you what we have found with membrane vents. So we've been conducting a very long-term outdoor field study in our facility near Munich, Germany. We want to evaluate these vents over very long periods of time. So we have these identical enclosures that are exposed to real weathering conditions, and we have different vent conditions and even a sealed but unvented option in there. We're actually past the 8th year of our study of this test, and there is a field study guide that we can share with you. The results are quite clear. The enclosures with the vents keep the pressure stable. It reduces the condensation, and it remains protected from the outdoor environment. The unvented enclosure that is sealed is exposing high pressure to the stresses and could actually result in a failure. I'd like to show you now some of the output from the study. So let's look at 1 year at the 8th year of the study, a full year period. So you can see that this graph here in the red is the pressure trend for a sealed but unvented enclosure. The outdoor environment is changing in the black line. So since this enclosure is actually sitting on the rooftop, it's heated by the sun and cooled by the rain and snow and wind. So these increases and decreases in pressure is related to the increases and decreases in the environmental condition. So you can see that the general trend in the winter and in the fall is higher pressures, and as it goes through the summer, it gets a little bit cooler. Actually, I have it the other way around. In the summer, it's warmer, but the pressure is higher, and in the winter, in the middle of the graph, it's actually a little cooler, and the pressure is a bit lower. There's a couple of gaps here. That was from we wanted to actually inspect the boxes and make sure the pressure sensors were working correctly. So that's where those gaps are. So let's just take a look at the pressure now. So this is the red line from the prior graph. And I've actually drawn a couple of dashed lines here to represent 70 millibar or about 1 psi of pressure differential, which is very common for a limit on seals for outdoor enclosures. Now, these local peaks of the high pressure and low pressure actually are more related to the daytime and nighttime temperatures. So you have the heating in the sun and the summer sun, and then cooling at night. And these are representing peak pressures that are greater than what the seals can endure over long periods of time. This would eventually lead to seal failure. Now I'm going to show this line here in yellow that is of a open hole. So this is a vented but unprotected enclosure and represents the best pressure equalization that you can hope to obtain. There are no rapid pressure changes from each day, and actually there's no trend in the pressure equalization, in the pressure response from warm summers and cool winters. So like I said, it's the best that you could hope for. Now I'd like to share what a GORE vent that's overlaid in green, and the yellow line is just behind there, is mimicking the open hole. The pressure trends are the same. The GORE vent actually tracks with the pressure equalization of an open hole. The key, though, is that the membrane vent will protect from that dust, dirt, and water. And like I said, this is the 8th year of the study, so this vent has been out there for quite some time, and we're now entering our 9th year, and we'll continue to update on our progress with this study. So lab tests and field trials are really good indicators of real-world use, but I want to share 2 brief stories from our customers' real-world use of how vents can alleviate their problems with sealed and unvented enclosures. So this is a story about a customer who has an antenna-aware altitude sensor, or AAS, that's permanently mounted to the top of their antennas, and that helps them make sure the antennas are aligned. These things require a solar tracking and gravity-based orientation, so it's really important that they stay clear and that they do not have any water inside, which, as you can tell from the center photo there, this unvented but sealed enclosure did actually have. The challenge for them was to actually clear that condensation, and what they did is add a GORE vent, and you can see on the right-hand photo, there's a black dot there that actually is where the GORE vent was added. And that cleared up the condensation that was forming through those cool nights where there was a lot of humidity. The second study I would like to share is a manufacturer of tracking motors. Tracking motors for solar voltaics are used so that they can orient the photovoltaic panel to the sun and get the optimum amount of solar radiation into the panel, and obviously the optimum amount of energy production. These solar panels are exposed to the outdoor environments. They're on the solar fields, usually right next to the panels. And as rain and snow and sun hits them, they get exposed to all those conditions that an ingress protected device is meant for. Now, one of the big challenges is that these operate a little bit every day, a little bit every hour. So they will operate for a minute or two as the sun moves position, then they'll operate a minute or two. So they have a high cycle time, but not a lot of operating time. Now, you can see in the middle photo here, we had a motor that was unvented, but sealed, and began to get moisture and dust, dirt into the motor and failed pretty quickly. The second photo there, you can see it looks clean, and after at least a year of operation, this was torn apart. Now, this environment with all the dust and dirt kept the membrane vent kept out the dirt and water, but the motor looks practically new. So now I'm going to turn this back over to Timo to summarize our discussion.
All right. Thank you, Matt. I will take it from here now and guide us through a short summary from today's session. So let's return to the slide from the beginning, because it really gives a good overview about the main functionalities of a pressure vent. So we heard that the vent provides long-lasting protection for electronic enclosures. by balancing pressure and reducing condensation. With this, it will also meet IP ratings from IP64 through IP68 and even up to IP69K. We also heard from Matt that tests according to the environmental standard IEC 600-68 are met, and that this provides assurance of durability in varying temperatures, humidity, and salt-laden atmospheres. Finally, I want to mention that we can partner with you in finding the proper vent solution based on your design requirements. And with our testing capabilities and simulation models, we are more than happy to support you. And if you have triggered any thoughts about your devices and designs, we are more than happy to help you also here. And last but not least, I would like to mention our upcoming webinars. Moisture management, we will have this with EE World on November 20. And then on December 4, we have an open panel session with us. And finally, I want to say thank you for listening today and EE World for hosting us.
Our pleasure. Thank
you.
you very much. Yeah, thanks. Timo, Matt, thanks very much. Gave us a lot to digest there, so hopefully you all know that you can ask questions at any time. We will take your questions right now. We'll get to the first round here, but do remember that even if you're watching this on demand, you can ask questions from our experts. They'll get back to you, and we'll try to get to all of the questions. If for any reason we don't, you'll hear from our sponsors, and we'll get those questions answered for you. So, gentlemen, first question. What are the most critical factors to consider when designing enclosures for harsh environments? You mentioned in this presentation what can happen when the enclosure is under certain conditions. So as a designer, what do they have to think of when they're designing for harsh environments?
So I can take this, Matt.
Yeah, please.
So from my perspective, the most critical factors, I think it's the definition of the ingress protection. So what level should your enclosure be? It's also about material durability. So what material you are choosing. It's about the material must be corrosion resistance, but also UV resistance. And then also it's about moisture management and thermal management. Yeah, and a well-designed enclosure should have a good balance between protection, manufacturability, and it should maintain the reliability that it really protects the enclosure on the long run.
Very good. Thank you. Okay, next question. What are some common applications for vents, and where do you see the most need?
Well, I can speak to that. Vents are used in many, many electronic devices that are either outdoors or in just harsh environments. One area that you may not think about is streetlights. Streetlights have moved from the old sodium bulbs that look orangish to LEDs, as our homes are now using LED source streetlights, and that has used a lot of vents to equalize the pressure with the drivers and the LED boards, the circuit boards. Other devices that use them are telecommunication systems. They've used them for quite some time. So the power amplifiers and the antennas, and just as the one example around the antenna tracking, the antennas themselves would use a vent. Timo, I'm sure you have a few others that you've come across too.
Yeah, like you said, many applications, but there are also ones like drones, for example, we in the energy field. So solar panels and solar inverters. So we really have a broad range of different industrial applications where our solutions are used in.
Yeah, that makes sense. And all this design goes into these incredible devices, and I'm I'm wondering if sometimes it's an afterthought to say, oh, we need to enclose these really well. So this springs to mind a couple other questions, but let's keep going with our attendee questions here. So gentlemen, when would you expect to see problems with your enclosures in the field? Now, I don't know if it's your, as in GORE's enclosures, or as a designer, when would you expect to see problems?
I can take this.
Thanks, Timo.
So I think so. If the enclosure is not properly designed for its outer use, I would expect that in the really early phase, maybe within the first 12 months in the field, issues can occur, and this can be moisture ingress from sealing failure, such as condensation or fogging, and even also early corrosion, which is also caused by improperly compressed gaskets or inadequate or not proper pressure equalization. And likely more on the longer side, when you think about 2 to 3 years in the field, I would expect that aging effects from UV radiation or also from thermal cycling become more apparent. Especially when you think about plastics enclosures without UV stabilization additives, or metals which are exposed to salt or to a very chemical environment without proper corrosion protection. But yeah, as said, if the gasket or it's not pressure balanced, I would expect within the very few months in the beginning, moisture ingress mainly would occur. I don't know, Matt, do you have anything to add to that?
I think if the question also talks about if you're using a membrane vent that's improperly sized, what might you see? Yeah. When might you see the failures? And that would occur fairly quickly. If it's undersized, then the pressure peaks that occur would look like a sealed but unvented enclosure, and you would stress those seals, or the vent itself does not have the robust protection against high pressure spray. You would see that relatively quickly if the environmental conditions are, if someone hoses down or sprays down the device, if it's on an outdoor like a tractor or something like that.
Okay, great, thank you. Next question. What are the best materials to use for an enclosure that's going to be in the field for an extended period of time? Is there the best case, use case?
I think it's what's best for the device. GORE membrane vents can be used on metal enclosures. For example, if it's a power amplifier that has a lot of heat that needs to be dissipated, so an aluminum structure is typical in that. Whereas if you have something that's lighter weight requirements, ABS or polyester, polycarbonates are often used for electronics, and both of those can accept membrane vents very easily. And really, it's just tailored to what the application is. If there probably is one area to avoid is maybe super slick environments where they're heavily painted, but typically the surface energy of those paints are well within an adhesive style vent and don't typically cause a problem. So I think you have a wide range of materials that you can select from and still get a membrane vent to be integrated easily.
Okay, great, thank you. Okay, so what's the next question here is, what's the life expectancy of the vent once installed? And I guess we should just assume in this question that barring some odd force of nature, what is the life expectancy of the vent itself? And if it's properly installed, I would probably assume, yes?
Yeah, I agree. So it depends on several several things. For example, it depends on its application, if the installation is well, and like you said, variable environmental conditions under which the whole device is operating. But in order to address this, this is what Matt presented, we conduct our vents, rigorous tests. We are following this environmental standard because with that, we really want to ensure that no matter if the device is installed in, in Asia, in Middle Europe, or even in Alaska, where it's really cold, we address this with our testing program. Internally, we name it fitness for use, which is, the vent should really do what it is supposed to do, and that in all kinds of environments. So we have this rigorous testing, and this is really demanding the materials. And with that, we want to address a long life, a long reliability of the vent in the field. It doesn't matter in what conditions.
Okay, great. Well, then the next question should follow, I would think, is then where should the vent be installed, and does it matter? I'm going to assume it kind of depends on the enclosure, but maybe not. Where should it be installed, and does it matter?
Yeah, so the vents, we generally like to have the vent installed in an area where you're going to have any rain or snow run off of it. So, for example, if you place a vent, a membrane vent on the very top of an enclosure, and you have rainwater pool on it, it's going to be tougher for the pressure equalization to occur. It's still possible. So we prefer to have it, say, on a vertical surface. It doesn't have to be perfectly vertical, or perhaps on the bottom of the enclosure. But for devices that maybe are rotating, say like a floodlight, we can have vents that are installed near the top or on the top, as long as we talk to the end user and understand, well, is that at the low point of the top surface, or is it slightly raised? There is actually some importance when it comes to the moisture management piece, and we're going to talk more about where you want to place the vent relative to moisture management in the next webinar.
Okay, great. Thank you. There's your teaser, folks. All right, so the attendees asking, they said they have open speaker and microphone ports on the device that needs to be protected from water and dirt. Can I use a vent to cover these ports? But then if you do, what happens to the sound quality?
Yeah, so you can use a vent, but not a pressure vent. So we differentiate. Okay. We have developed our own product portfolio, which is just addressing acoustic applications. And these membranes are specialized to provide a good protection. Also, we are fulfilling IP ratings, and in a lot of applications, submersion into water is really important. But at the same time, the membrane protects for water ingress, but at the same time, the membrane should allow the acoustics to go and flow through. So there should be not a lot of dampening or insertion loss caused by the membrane. And for this, we have developed our own product portfolio called acoustic vents. And typically, the sound pressure level, or the loss of sound pressure, is smaller than 2 decibel over its frequency spectrum. So yeah, but it differs. We differentiate between the pressure vents and acoustic vents.
Okay, great. So Eric is asking, what are the, I'm just going to kind of paraphrase this, what are the variants between different pore size or porosity specs? I'm guessing, just asking, do the vents have different porosities?
So yes, the vents do have different porosities or pore specs, but we find that for pressure equalization, the pore size is less impactful than actually the airflow and its ingress protection and its what we call water entry pressure performance. When you start talking about pore size and pore specs, I start thinking about some other aspects around diffusion and how water vapor or gas sensors may be operating. So that's where the more interesting discussion can be had around pore size and porosity, is around actually the use of a membrane vent as a gas sensor protection device. So we can talk more about that if you're interested, Eric, about what that may mean to you.
Okay, Eric, you heard him, and feel free to reach out again. And actually, we've got another question from Eric, and he's wondering if GORE offers the stick-on type, such as a round Band-Aid.
Yes, so the adhesive vents, yes, that's what we do. We have
Okay.
standard sizes, and we do make also some custom sizes as well.
Okay, great. Eric says thanks.
Oh, welcome.
All right, audience, we have time for a few more questions, but just a reminder, you can still ask questions, and we will get back to you if we don't get to all of them first. So, George is asking, do your seals revert the conditions? I saw one with rust, but then it looked like it was brand new. How is this possible?
Yeah, yeah. So let's go to that slide. So you were asking about this image here. So in reality,
so, yeah.
the end user actually had to replace these motors because they would go to failure. And in the redesign of this, they actually said, okay, well, let's integrate a membrane vent. And then they looked at it afterward and pulled one apart to solve the problem. So that photo on the right is actually a new motor that had a GORE vent after a period of time out in the field, whereas the left one was a quote sealed but unvented enclosure. So there is no way to actually remove the rust and revert it back to clean. We'd love to be able to do that, but obviously the membrane vent's a barrier. It would not make the rust go away.
So then you would want to have that membrane vent in there in the first place, as opposed to getting it out in the field, having to deal with the additional cost and reinstalling it. Yeah?
Yes, absolutely. So these are things you want to consider as you're designing your enclosure or your motor before you start to see these problems.
Yeah, for sure. Okay, we have time for just a few more questions here. So there's another question from our attendee asking, are the adhesive vents available in any other shape besides circular?
Yeah, so we do have a standard portfolio that includes mainly circular sizes, but we also have the possibility to think about custom shapes, custom geometries. Typically, we need to understand like the volume and the size, but generally speaking, custom sizes, custom geometries, it's possible to realize.
Yeah,
if you have, if you have a requirement like this, yeah, we are more than happy to review it. Yeah.
And here's some really funky designs with holes. So yes, it is possible. We need to discuss, what those requirements are.
Okay, excellent. Thank you. The attendee has asked, I'm seeing fogging and condensation in my enclosure. How do I stop it? I'm wondering, is it too late by the time, personally, I'm asking on top of that, is it too late by then? But anyway, if you're seeing the fogging and condensation in the enclosure, how do you stop it at that point, if at all?
Yeah, so there are several points which, typically we are reviewing when it comes to condensation and fogging. We explained that, and we also have the webinar which goes really into detail about moisture management. It's on one hand, it's the vent. The vent helps that water vapor can diffuse in and out, like we explained, and that will help like keeping the moisture level lower to reduce the risk of condensation. The other thing is also you could like check your materials, because plastic materials are able to absorb water and release water moisture. And also certain plastic materials are permeable for water vapor. So water can like diffuse through the material. So as said, we talk more about that in our webinar on November 20, but there are several things you need to review and to check. A vent is really helping to manage the moisture and to keep it on a lower level. This is we have several data which are showing that. And
yeah, I'd like to offer the other idea that if there actually is a seal failure, so if you have a vented,
Yeah.
excuse me, unvented but sealed enclosure, and you're being sucked liquid water inside. That's when you're going to get the fogging. That's how you'll see it first. And adding a vent or a way for the water vapor to escape will actually decrease when those condensation events occur and how long they occur. So we can share more about that in the future.
Okay, great. Well, at that note, talking about the future, and let's remind our attendees again, as Timo mentioned, there is another webinar on November 20th, and that's when we're going to talk about managing moisture in more detail. So you can register for that. You can go to eetrainingdays.com and register there as well. And also, we'll be talking to the experts on December 4th. So this is going to be a panel discussion. It's going to be your opportunity to ask, I was told, the tough questions. So get them ready and make sure that you register for these events. And remember, you could watch them in any order once you get they're all done. And you will see the URLs for registration should be in the resource center as well. We highly encourage you to join us again, join our experts again. And also just remember, keep asking questions. We will make sure that we get to them and get back to you. So want to just one more little survey, if you get a chance later, is to complete a survey for us, so we just know how we're doing so that we can also do better. And also, if you have other ideas for EE training days. And as I mentioned, you can submit questions in the Ask Question widget at any point, including on demand. So on demand will be available using that same URL that you got when you registered. And for those who are just registering, that's what you can use. But we do hope to see you back on the 20th and then the 4th. So gentlemen, any final thoughts, final words?
Well, thank you very much for hosting us and for listening to us today, audience. I really appreciate your questions and opportunities to share our knowledge.
Thank you very much.
Thank you, gentlemen. And just so you know, we're already getting feedback from our attendees that this was a great session and they're looking forward to the next one. So do your homework, guys.
Will do.
All right. Thanks, everyone. Have a wonderful day. Thanks for joining us for EE Engineering Training Days. We'll see you next time.
Thank you.